everyone, and welcome to week 2 and the module of the air we breathe. In this module we're going to talk about air for week 2 and air pollution in week 3. We are really going to set the foundational knowledge. We're going to talk about, for example, how to classify matter and how to use dimensional analysis, and those are just a few examples of what we're going to go over this week. And for now, we're going to go ahead and get started and into talking about air itself. So in this chapter, or chapter 1, we're talking about the air we breathe. And we're going to talk about what is in the air that we breathe, and can air be dangerous to our health, and how can understanding chemistry help us decide. First of all, why should we care about the air? It's simple as just it's what we breathe. And if you compare water to air, we can go days without water, but seconds, minutes without air. So we can choose not to drink a dirty puddle of water and walk away from it, wait till we get home, wait till we can buy a bottle of water, whatever, we can wait for it. Air, you really can't wait. You have to breathe or you die. And the simple way to think about it is the air we inhale, right? That air we inhale goes into our lungs and goes to the rest of our body. And that includes end organs or wherever else that air gets to in our body. And eventually that air comes out of us as an exhale. And when we think about air in general, here's a picture of Los Angeles County. Air pollution, for example, we call also smog, right? That's kind of a misnomer. Smog actually is smoke and fog, but we don't really have smoky or foggy weather too much in, for example, LA. But anyway, it's chemicals that are basically added to the atmosphere by natural events or human activities in high enough concentrations to be harmful. So air pollution is estimated to cause 2 million premature deaths worldwide every year. And that's from the World Health Organization. So when you think about it, the air we breathe can actually be toxic for us as well. Here is a diagram of the layers of our atmosphere. On the x-axis down here, you have the temperature. On the y-axis above, you have atmospheric pressure in millibars. On the y-axis, you have altitude in kilometers on one side and miles on the other. Now, one thing you should notice right away, when you're low down at sea level, which is about 0 here, when you're low down at sea level, you have the highest atmospheric pressure, which is around what? Here you have like around 900 millibars, okay? But as you go up, and it says 1,000 approximately, but as you go up in altitude, notice that the atmospheric pressure reaches about 0. It gets really low. So the higher the altitude, the lower the pressure. Another interesting thing about lower down here in altitude is the temperature. Notice the temperature right here on the map, or this diagram, is 0. So right here at the surface, we're looking at maybe 10 or so degrees Celsius. As we go up in altitude, the temperature lowers. It gets colder and colder and colder until we hit this point here on the graph called the tropopause. All right, the tropopause. And everything below the tropopause is called the troposphere. This whole region, about 10 to 15 kilometers to the surface, is the troposphere. Above that, we have the stratosphere, which, as you notice, is where your ozone layer is right here. As you increase in altitude, the temperature increases. And you see that inversion occur over and over again throughout our atmosphere. So the most important layer here is right by the Earth, which again we call the troposphere. That troposphere is where we breathe and we see the weather, and everything we do here is basically the 1% of all of that Earth's atmosphere. But it's the most important one to us because we live in it. If you look at the composition of dry air, most of it, 78%, is nitrogen, 21% oxygen, and 1% of other gases. Notice that this is a mixture. You have a mixture of nitrogen, oxygen, and other gases, which is basically a physical combination of two or more substances present in variable amounts. Now let's look at this graph here. This is the typical composition of inhaled and exhaled air. So your inhaled air is what your dry composition of air looks like, 78% nitrogen. You exhale 78% oxygen. So you're not really using the nitrogen, I'm sorry, not oxygen. You inhale 78% nitrogen, exhale 78% nitrogen. So you're not really using the nitrogen in the air. Now for oxygen, you have 21% oxygen, you inhale, and you exhale 16%. So there's a, 5% drop in the oxygen. So you use up some of that oxygen inside your body. Argon, on the other hand, is just 0.9 to 0.9. So you're not, again, not using the argon from the air into your body. Carbon dioxide, you breathe in 0.04%, which is not a lot, and you breathe out 4.0%. So that oxygen we use up in our body, and it gets converted eventually into carbon dioxide, and we breathe it out. And water depends, it's variable, right? Depends on if you live in the south where it's humid, or if you live in the desert where it's very dry. So it just depends. So the term we use to describe air, or what's in the air, is their concentration terms. And concentration, just to give you a reminder, is the amount of stuff you have in a volume, right? So the amount of, for example, oxygen you would have in a specific volume. So for example, parts per 100 is probably the easiest one to understand because it's the same thing as percent. So in the atmosphere, there's 21% oxygen, which means there's 21 oxygen molecules per 100 molecules and or atoms in the air. So that's basically a percentage, 21 per 100. Parts per million is even used for smaller numbers. So for example, the midday ozone levels reach about 0.4 ppm, which equals 0.4 ozone molecules per 1 times 10 to the 6, which is scientific notation for a million. We will get into scientific notation soon, so don't worry about it yet. Of molecules and atoms in the air. So it's 0.4 over a million, which is a very small number. But that could still be a toxic value for plants, especially. They get really sick in ozone. So ozone is a toxic chemical in our troposphere. Parts per billion is an even smaller number, right? So it's going to be, for example, sulfur dioxide in the air, which we get from burning fuel or wood or anything we burn. Typically we talk about fossil fuels, or carbon, or not carbon, what do you call it? Coal, which is from carbon. But anyway, we burn coal and you get sulfur dioxide in the air, and it should not exceed 30 parts per billion because it becomes acid rain essentially. What that means is 30 sulfur dioxide molecules per 1 times 10 to the 9, which is billion molecules and atoms in the air. So 30 sulfur dioxide molecules per 1 billion molecules in the air. So it's a very small number in comparison to the other ones above, but it's even at that small value, if it exceeds that, it can be dangerous. Now if we want to relate all of the numbers together, we can do that. We can convert them. So again, 21% means 21 parts per 100. Now I can actually times 10 to both sides of this, and I could do 210, which is 21 times 10, 210 parts per 1,000, which is 100 times 10. So 210 parts per 1,000. It means the same thing. It's the same concentration, but it's another way of, if you want to compare value to value of something that's in per 1,000, you can do that with this method. You can do the same thing here. You can times another 10, so it's 2,100 parts per 10,000. You could times another 10 by both, and it'd be 21,000 parts per 100,000. You repeat the same method, it'd be 210,000 parts per million. So again, all of these numbers are equivalent in terms of the concentration. But one thing you should note is the difference between parts per 100 and parts per million is a factor of 10,000, right? Because I had to multiply 10, 10, 10, 10, 10, 10 to all of these. So the factor difference is 10,000. So when you look at parts per 100 versus parts per million, you should understand that the values are significantly different. All right, so that is everything for this chapter, or for this week, I should say, in terms of our introduction. I hope you enjoy the rest of this module and learn a lot about the foundation of chemistry. And I will see you next time. Bye-bye.